functions, so they have to return maybes. If you want to combine with a regular function, then you don't use bind.
You do use bind, but you have to lift the other function into the, so you have to return the other function, which kind of, you can, there's basically in the monadic construct, there's a function that takes a function from A to B and turns it into a function from A to maybe B, so that you can use it in the...
Okay, yeah. Okay. You're right, but I'm thinking of return as taking a value, because it really takes...
It's something like lift, I think.
Oh, okay.
Lifting into the monad.
Mm-hmm. But normally you would do it with return. Return the result of acting with f on something, right?
Well,
you just lift the result. You don't have to lift the function.
No, you lift the function because it's easier than all the time kind of doing a non-monad, embedding a non-monadic expression, doing a let, and then returning that. It's
okay.
You can do both.
Yeah, that's a digression though. So this is this cascade of continuity. This is very important to sort of picture in your mind. So I'm acting with f on v. It returns a monadic result, the enriched result. And if it's nothing, I just bypass everything, go to the exit. But if it's just, then I call this lambda. That's my continuation. And this internally, again, calls v1. And it returns this result. I match it. I can return immediately, or I can call another lambda, and so on. And in fact, in Haskell, because you put this sort of stuff in the middle of this, so it's like bind is actually between this and this, they use an infix notation for this. And this is what you can find. If you are looking at Haskell stuff, you'll find this infix operator, right shift infix. You don't have to know this. This is, yeah. And this is the same code that I wrote before, except that now it's using the infix notation for bind. So it binds this with the lambda. Okay. And finally, the return function. This is a trivial thing in this case of maybe. But a return function has to be defined in order to complete the monad. So first element of the monad, there was this type constructor that creates an enriched type. There is bind that uses to combine functions that return enriched types. And finally, there's return, which just takes a regular value and enriches it. Okay? And in this case, enriching a value is just saying, okay, well, it's just v. Right? Okay, let me see what's next. Oh, the do notation. Just for completeness, okay? This code is pretty ugly. Even for, yeah. So there is a special syntactic sugar to yes?
What is the type of compose? So there's a case when some function call returns nothing. What is that would be a different? What is then the return type of compose?
It's maybe.
So it's maybe or v3, which is not a maybe, or it has to be a maybe.
No, v3 is not a maybe. Return v3 is a maybe, because that's what
okay, because it's the magic return and not
yeah,
okay.
Yeah. It enriches it. Yeah. Mm-hmm. Exactly. Man, I'm gonna finish this, and so the do notation is just syntactic sugar. What is interesting about this is that it looks much more now like what we started with, this magic code, right? I told you this magic do. After which you just write regular code and don't see the maybes, don't see the errors, nothing, you know. This is a special notation which accomplishes this. The whole plumbing of binding is hidden from you. Unfortunately, I won't be able to do this in C++. Yeah?
So, this is specific to the bind that we just generated, right?
What is specific to bind?
So the bind function object that we created a couple of slides back.
Mm-hmm.
So this notation then tells me that it's that bind is some that bind is.
Are you asking about do notation? Do notation works for every monad, and every monad defines bind.
Oh, so bind is special.
Yeah, monad has type constructor, bind, and return. So do notation works for every monad. And this is C++ do notation. Okay? Function compose calls f with v, it returns v1, calls g with v1, returns v2, and finally returns v3. Looks exactly like this, right? Oh, one-to-one correspondence. Except when you call compose, you do this thing, try catch. Okay? So this whole thing is also implemented in C++ using exceptions. Okay, exceptions provide more functionality than maybe. Okay? But the principle is the same. In C++, you just do this with exception. You don't really need optional, you don't need maybe, you just do exceptions, right? And this is your do notation in C++. The difference is, you cannot generalize it. It only works for exceptions. The do notation in C++ only works for exceptions. There is no other monad in C++ that's built in. Plus, in Haskell, you have very strong type checking, which in C++ you could say, oh, the type checking would have to include the exception specification, right? If we had exception specification, right, which I think was dropped, right? So, because it didn't work really. So if we had exception specification and the compiler enforced it, then it would be part of the type system. But it isn't. Okay, am I done? Yeah, this is a good point to stop. Okay, so you got some time for settling these ideas in your brain, maybe rearranging it a little bit, because the next step is building on the previous stuff. But we'll be repeating the same ideas over and over, so they will maybe you'll understand them better on every iteration. Yes. Are we already recording?
Okay.
Are you recording? Yeah?
Yes.
Okay, good. Okay, so this is really what I wanted to talk about the state monad. Maybe monad was just to illustrate in a simple example how you bind things, how you create these enriched types, how you turn a computation into a function that returns enriched types. Okay, but state monad is really the one interesting. So this monad is used to deal with computations that use state. So for instance, they could be using global variables, they can modify them, they can have static variables, and so on. So these are definitely not functions because they don't return the same value every time. And it turns out that this kind of computation that deals with state can be modeled by a function. You can turn it into a function, but you have to explicitly pass the state. You know, you encapsulate the state into an object, right? You just pass it to this function, it deals with the state, okay, and then maybe modifies the state and returns the modified state. Now that's perfectly functional, right? And if the computation was returning some particular value, you just bind it with the new state. So it returns a tuple, right? New state and some value. So this is the simplest of these functions that you can think of. It actually doesn't take any arguments except state, right? And it returns a tuple state and some value of arbitrary type t, depending on what computation you were dealing with. Okay, so this is called an action. Okay, and we'll be talking about actions a lot. Takes a state, returns a tuple. Now, a computation is not really an action, because a computation will take some additional arguments, right? I mean, you start with a computation that takes a bunch of arguments and returns a value and deals with state, right? So this doesn't really fit in our monadic world where you take a computation and you just change the return type into something. Here you not only change the return type, you also would have to pass the state up front together with other arguments. This is not that easily generalizable. And composing such functions is also very manually doing this. It's all possible. So you take any computation that has state and you can turn it into a bunch of functions that take state, return state, plus all other arguments and all other values. You can do it manually. You can unpack stuff at the end, pack them back, and so on. So it's all possible, but it's messy. So ideally what we would like to do, and in Haskell they always strive for the ideal, okay, and then see, can it be done using functions? So we would like to hide the state. This is what we do originally in imperative programming, right? We just hide state. You have a function, the so-called function, right? It accesses state. We don't know that this function accesses state unless we're looking at the implementation, right? So it would be nice if we could sort of hide the state, because but at the same time, if we hide the state as we do in imperative programming, we lose the type safety, right? Because now you don't know that the type of the function doesn't tell you that it's using state, right? And what kind of state it's using. Is it modifying the state or not? Plus, if you are in Haskell, you would like to have a sequencing of actions, right? So you do the first action, it modifies the state, then you call the next thing with this modified state, right? It does its stuff, and so on. Now, if you hide the state, then suddenly you have functions that don't depend on the state, you don't see that. And if you say, do this function first, and this function second, and the third function next, Haskell will say, ha, I know better. I'll do the last function first, okay, then go to the first one, then do the middle one, and sometimes I won't do anything because nobody's using the result of this function, because all it did is modified some hidden state, right? So these things, we want these things to be done, but on the other hand, we won't have notation which doesn't show this. And the solution is this. Separate two worlds. One is the composition of things. So when you have multiple computations that deal with state and you want to do them one after another, do this combining of these things separately. And then, when you are done with this combination, they will produce something which we call action. And then you call this action with your state, and it will return you a new value and a new state. Yes?
Say you want to call the same function 1,000,000 times from the state in sequence.
Mm-hmm.
You know, what happens then? You have to sequence. You have to have some sort of list where you have 1,000,000 entries.
Well, in Haskell you use it recursion, right?
So
instead of loops.
You can put recursion into this.
You can put recursion into this. Yes, yes, yeah. You can call a recursive monadic function. Mm-hmm.
What if you don't What if you don't know when it's going to terminate as well? For example, it terminates depending on some result.
No, the recursion will actually happen when you are executing the action. Recursion does not happen. The recursion will just be encoded into this action.
You can encode recursion.
Yeah. And the result of this is a statement. And I think I have the picture that I did during lunch. Because this is maybe a little hard to understand. So the starting point is computation. Computation takes a bunch of arguments, returns some value. Oh, that was type A. Okay, it disappeared. Okay, some value of some arbitrary type A. Right, and whilst doing this computation, it's accessing some state, possibly mutable state, possibly it mutates the state, right? So there is this cloud here, the state. It comes into play somehow, not clear how. Okay, it depends on the implementation of this computation, and finally it produces a value. So this arrow here are the original arguments to the computation. And it returns a value. Now we split it in this way. We turn this computation into a monadic function. This monadic function takes some arguments, the same arguments as the computation. But it returns an enriched thing called an action. It doesn't return a value. It returns a function. And this is the action. The action that's returned by this. It takes a state and returns a value of type A, plus it returns the modified state. So the state transformation is done here by the action. Whereas the implementation of your algorithm, implementation of your computation is done here. It's like here I'm compiling a program to do this computation. The resulting program is this action. I ran this action and I get my result. So this division here, splitting in the middle, is the state monad. And my goal is to turn this into C++ compile time computation, and this into the runtime part of my computation. This is why I need monads. And this is what Proto does.
Why wouldn't most of the work that's actually done in the monadic function be done in the action itself? So how do you separate the parts? How do you decide which part goes in?
The part that needs state has to be executed here. The part that doesn't need state can be done here.
Yeah, so it's done by the programmer that, okay, I have to split it into these two halves. Right? It's not...
No, actually the thinking is different. The thinking is like this. You think about computation. This is what I'm going to do. Using state, okay? This computation is some algorithm. It calls some other functions and so on, right? You take this, you translate it into a monadic function. So this is how you get your monadic function. And this function will return an action, and then you run this action. So there is a correspondence between these two. This is your concept that you are trying to implement. You implement it as a monadic function. I mean, you have to see examples, right? But this is the main idea. And actually, I won't be showing you the state monad because I don't have the time. So instead I will show you an example of a simpler monad, which is called a reader monad, which deals with state exactly the same way, except that it doesn't modify the state. So a lot of things are simplified. For instance, the action doesn't have to return the state because it hasn't modified it. The state remains the same. Okay? So it's a simplified monad, and in particular I want to implement my own version of a reader monad that's used only for the purpose of proto. So this is the monad I'm going to implement. It's like a state monad with read-only state. So I will start with expression trees, okay? These guys who were at the Joel's talk or know about proto from other sources can recognize this as expression trees. I'm starting with expression tree, and this is an example of an expression tree. And this expression tree is constructed from 3 types of nodes. Constant nodes, which correspond to integers. We're dealing with integers only, okay? No floating point, and then just integers for simplicity. There are 2 placeholder nodes, arg1 and arg2, which corresponds to arguments that will be passed later. The values will be passed later as state. Okay? And I'm not going to modify these arguments, although in proto you can pass them by reference, I guess. And it has plus and times nodes. Just simple arithmetic. Minimum example. It's a toy example. State in this case will be this list of 2 arguments, right? 2 values that I'm going to pass. So it's like I'm constructing a lambda of 2 arguments, and when I'm done, I'll be executing this lambda by passing it P values that will be put in place of arg1 and arg2 in this expression, right? So an action in this case will just evaluate the corresponding expression. And these expression trees, they are not part of the monad itself. These expression trees will be just what drives the composition of actions. Okay, so this expression is like my source code to the program. Give me a tree. This is a source code. Okay, then from this tree I compile a program, which is the action, and then I run this action. Okay, so now we have a conceptual model of this stuff. So let me start. So first I do this in Haskell, then I'll do this in C++. So in Haskell, my expression tree, it's just a tagged union, right? So I'm listing different kinds of nodes, and these are type constructors for these nodes. So a node or expression could either be a const that takes an integer as an argument and stores it. It could be a plus that takes 2 expressions, arbitrary expressions. So this is recursive type definition. It could be a times that takes 2 expressions, or it could be placeholder arg1 or placeholder arg2. So that's my tree. This is how we define a tree in Haskell. Very simple. Right? It's a recursive definition. Yes? What's the state? The state will be, I'll call it this type args, and it's a list of integers. Now I really need a list of 2 integers, but I'm being sloppy here, or maybe I'm being very general here. Yeah, in the future maybe I'll need more arguments. Who knows? But this is the simplest data structure. I don't have to explain more complex data structures. So just a list of integers. That's my state. Okay, these are the values that I will be passing to my expression, the lambda with placeholders. An action in the reader monad. You remember an action in a state monad, that was something that takes state and returns a tuple, modified state and some value. Here I don't have to return the state, so the action is even simpler. It takes arguments, give me the arguments, I return you a value. So it's sort of like evaluates an expression. You know? Give me the two arguments, I'll give you the value. Okay, now the monad. The first component of the monad is the type constructor, right? So my computation took some arguments and returned some value of type A. That was the computation, the upper part of my picture, right? I'm turning it into a monadic function that returns a type that's the enhanced type. Before, the computation returns just the value of some type A. Now this guy is a function that takes state and, forget about this, returns a value. In reader monad there's no state. So it just takes state and returns a value. So this type, the function type, this is my enriched type. So give me any type, and I will enrich it to be a function returning this type. So this action, in Haskell, this action has to be encapsulated into a new data type. And this is for reasons that have nothing to do with anything, just that Haskell has to do type inference. So it has to have a new type for this. So I'll call this new type program, prog, of type A, meaning program that returns A. Returns, let's say A is an integer. In the rest of the stuff, this will be an integer. So it's a program that calculates an integer. And there's a type constructor, a constructor that I call PR, that takes an action. So it takes a function, right? A type constructor can take an arbitrary type, and in this case it takes an action. So once I have a program, I want to run it. That means calculate my expression. So I write an auxiliary function run that takes a program and pattern matches it to extract the action. So it extracts this part, the function, the action, right? And then just calls this action with the arguments. Very simple stuff, right? So this is executing my expression. Now monadic functions. Monadic functions are these functions that return this new enriched type. They correspond to some computations that used to return some type. Now monadic actions actually instead return this enhanced type. So I have to give you examples. And this is the first example is very important. It's useful. The other is non-useful, but just for the sake of argument. The first monadic function is getArg. The computation that corresponds to it is just give me the nth argument. So I can call it with 0, it will give me the first argument. With 1, it will give me the second argument. So just extract the argument, right? But this function is supposed to return an action. It actually cannot extract the argument itself because it has no access to state, has no access to these arguments, right? It doesn't take any state as argument. It cannot. So this function is to produce a promise of extracting the argument. This function says, man, I don't have it right now, but I promise, as soon as I get my paycheck, you know, the argument, I'll do this for you, okay? So a function returning a function returns a lambda, right? So I have to create a lambda. So this lambda, this promise, I encapsulate it as a program, and this is the action, the lambda. So when I get the arguments, man, what I'll do with it, I will take the nth element of the argument list. Okay, this is Haskell, nth element of a list. This is how you get it, okay? So that's our first monadic function. The second monadic function is really trivial. I just need to have an example. So it's a monadic function that takes an integer and returns an action that will return double this integer. It will actually ignore the state. This is why it's so trivial. It will ignore the state. It really doesn't need the state. Right? So this is my monadic function. Double takes an argument n. Okay? And this is, like, think about the computation. Takes an argument n and returns 2 times n. Now you lift it, so it takes an argument n and returns the promise of returning 2n. Right? So it returns a lambda that takes arguments, promptly ignores them, and returns 2 times n. And of course you can see that this lambda is actually a closure, right? So it grabs this n. Where does it get this n? From here. So this function grabbed this n, stored it somewhere, and when it's called, it just reaches for this n and returns double it. Yes?
So what is a double there for?
What is it for?
Double n equals, so what is the double, what is the function of double there? Because
it looks like a data type.
Double. No, yeah, there is no double type in Haskell.
Oh, I'm sorry.
This is just a name of function. Maybe I should call it double me. Okay? Yeah, no. Yeah, it's just like return in Haskell is completely different thing. Double means completely different thing.
That's a mess.
What are you doing there?
Okay, now the second part of the monad is bind. Okay, so I have 2 monadic functions. These are functions that return promises. They don't really do something. They return promises to do something. But I want to combine them. And this is a good example of combining these functions because the second one depends on the result of the first one. So I want to do something like the crazy thing, you know. I want to take the 0th argument and I want to double it. Okay? But when I'm calling getArg with 0, I don't get this value. I get a promise to get this value. And here I have another function that takes a value and returns a promise to double this value. How the heck do I combine these? Right? When I combine these two, when I bind them, I want to get a function that will do both things. The one action that takes the 0th argument, doubles and gives it back to me. Okay? So let's analyze this. GetArg with 0, it's a monadic function that creates an action, right? So if I want to bind it with the second function, actually bind doesn't take a monadic function, it takes a continuation. This is the rest of what you are supposed to do. What you are supposed to do when the first action is finished, you're supposed to take the result of the first action, okay, and do the rest of the computation with it. That's my continuation, right? So when I'm doing the binding, right, I don't have this function yet. But when I will execute the action returned by bind, I will have the argument. And then I can actually chain them. So bind, in this case, will take the action. That's the action returned by getArg0, we've seen in the previous slide. And the continuation, it is a function that takes some value, some v, okay, so it's a lambda of v. This v will be later substituted by the result of the first action, right? Right now I don't have it, but I can write a function that takes it, right? So I write a function that takes the result of the first action and doubles it. And what the whole bind is supposed to return, it's supposed to return a new action which will do both. A combined action. Okay? So it will return type prog B. The first action is prog A. The continuation is something that takes A and produces a prog B. And here's the picture, okay? So I have two monadic functions. One monadic function, another monadic function. I want to combine them, okay? The first monadic function takes some arguments, returns an action, which takes a state and returns a value. Now my second monadic function, okay, it really wants to take this value here and put it as an argument to the second monadic function, right? But this argument will only be valid when this first action is executed, much later, right? And this monadic function will return an action that takes a state and returns the value, right? So this big box here is my continuation. Since I don't have this value that I will need, I will just write a function that takes this value, and when it's called, it will do this. It will do the rest for me. Okay, so this is my continuation. So bind takes this result, okay, and the continuation, and it will produce another action that combines these two. Mm-hmm. Yeah.
Doesn't bind take the action and the continuation and not the value and the continuation?
Bind, okay, bind
Takes the action.
Takes this action.
Right.
Yeah. This is the argument to bind.
Yeah.
But it is a result of some monadic function. In our case, get arg0. Get arg0 will produce this action. Now we bind this action to this continuation. Yes. So how do we construct this bind? And this is the heart of the problem. Okay? So we start with this. The bind should return an action, right? So that we know that. So since it has to return an action, it will actually return a lambda, right? An action is a function that takes arguments and produces some value of type B, right? And this forms an action that will be returned by bind.